Hi guys, this is number 14 for AP Physics C for Unit 7. Okay, so there are three parallel wires. This is what the problem gives us, and they're separated by some distance, capital D, and some distance, lowercase d. These don't take this at face value. I have no idea what the values of these distances are. And then these are labeled wires 1, 2, and 3, and they each have currents I1, I2, and I3 going through them respectively. All right, this is all the problem gives us. And so we can start with part A. So if capital D is equal to lowercase d, how should the magnitudes and directions of currents I1 and I3 compare if wire number 2 is to experience a net magnetic force of 0? So other key point here is net magnetic force should be 0. So this is a difficult problem, actually. It took me a while to understand this, but I think I got it. So let's first address this issue, the net magnetic force being 0. If we just draw wires 1 and 3, in order for the net magnetic force to be 0, wouldn't you say that these forces, the magnetic forces, so the forces generated by the magnetic fields, which are in turn generated by the currents going through wires 1 and 3, those forces should be opposing each other, right? Because then if they're equivalent to each other, that's the other niche thing. If they're equal to each other and they oppose each other, the net magnetic force between them in this area, which is where wire 2 is located, that net magnetic force is 0. So we want this to come true. Right. Okay. So let's go into, now that we know that, let's go into the first part of the first detail in the question, which was D is equal to D. So uppercase D is equal to lowercase d. What does that tell us? Let's use Ampere's law really quick because it looks cool and it will prove something even cooler. So we have a closed integral of b dot dl, and it's equal to mu naught times I. Mu naught is just some constants of like free space or something, and I would assume you guys know the other things. So with that, we can integrate, and I know that if you prove like certain things, like for a Solaroid or whatever, you will get dl to be, you will integrate dl from a limit that would prove like, like a circle or something like 2 pi r. But here I'm just going to integrate to L. So I'm just going to do some quick math. This becomes L, and just it's an indefinite integral, and mu naught I over L. You just divide over that. Hopefully you guys can follow along. And if D is equal to D refers to this L here, then we can totally ignore this because it's just a constant now. They're both the same. They both exist in both equations for B1 and for B3. And mu initial is also a constant that exists in both B1 and B3. So that can go away. The only difference now lies in the fact that B1 is equal to I1 and B3 is equal to I3. And so if we want these to be equal to each other, we would need the and you're like, well, okay, let me just really quick go over why we want the magnetic fields to be equivalent to each other. And that's because if we learned that the force is equal to, give me a second, it's equal to Q, hold on, oh, right, no, I, L cross B, or if we're just taking it at a single point, Q, V, B sine theta, right? So the important part here that we need to look at is B. The magnitude of B needs to be the same for both of these in order to achieve this force 1 to be equal to force 3, and thus, I'm just going to get rid of all this. Thus, we can assume the following, that I1 is equal to I3. So therefore, we know that I1 needs to be equal to I3 in order to achieve this situation with a net magnetic force of 0. Now, the second part of this problem lies in the direction of these currents. And this is a little more tricky. So we have wires 1 and 3 again. Again, I'm ignoring wire 2 because all we care about is this area here in between them. And I'm going to assume directions for wires 1 and 3. I'm just going to assume them. I'm going to assume that I1 is going up and I3 is going up, okay? I'm not saying it's right, but I'm just going to assume that about them. So with that, we know that a magnetic field is generated by a current being run through a wire. So using the right-hand rule, and I'm going to draw that here, the right-hand rule stipulates that the current should be, you just use your thumb and point your thumb in the direction of the current, and you curl in the direction of B. So here, current is going up for I1, and thus we get a counterclockwise direction for B1. So what's significant about this is that we need to pay very close attention to a single point in this parallel for these parallel wires, and that single point is on a wire. So let me explain that. A wire with a current being run through it is essentially a bunch of electrons that are flowing. This is not conventional current that I'm referring to. That was for RC circuits and stuff like that. This is different. This is what current is in real life, which is electrons flowing from one point to another. And each of these electrons has some velocity. And this is where the the important distinction can be made, is we can use a right-hand rule that we learned earlier, which is this thing where you like make your hand look like a gun, but it's not. It's just this weird like bird thing. So you have your thumb referring to the magnetic force, which as you can see is going to be very important in proving this force 1 is equal to force 3 business. So your thumb refers to force M, your index finger refers to the velocity of the particles, and the particle, singular, and the your middle finger refers to the magnetic field. This is all at a single point. It's really important, because you may be like, oh, well, B is going in a circle around the wire. Well, that's right, but this particular rule is just referring to a single point where B is tangent to that circle. Okay, so why don't we take this and apply it here? So we know that the current, let's just focus on I3. We know that the current is going up there. So I'm just going to draw another, wow, I just do it over here. I'm just going to draw another finger, and this is your index finger. This is the direction of I3, right? Remember, I said that the velocity of these electrons, the direction of the, let me write that. Let me put that in writing, just in case you guys didn't get it. The direction of the velocity of these electrons is the same as the direction of the current. Okay, I said it wasn't conventional current, but that's really an important thing here. So coming back to this, and we're applying this now. Coming back to I3, so we know that the index finger is referring to the direction of I3. So we point our index finger, and we should not be getting the side of our index finger or being pointed towards our face. It should be the part of your index finger with like lines on it and stuff, and it's like you're about to touch yourself. Like, I don't know how to explain it. It's like your palm is faced towards you, and if that's the direction that your index finger should be facing your face. Yeah. Okay. And with that, we can also get the magnetic field and the force. And if we do it like this and this, I'm not going to draw the rest of the fingers or whatever. I'll just do that. That looks really weird. Let's not do that. I'm just not going to draw the rest of the fingers. This is a stub. Okay, so this is I3. This middle finger represents B, and this represents the magnetic force. Now you may be wondering, it's like, what? But why is the magnetic force going outwards? This rule is being applied to electrons. So these electrons are going to be, if you remember, the magnetic force will be in the opposite direction of what you get from the right-hand rule. So actually, this magnetic force is not going this way, but as a matter of fact, it's going that way. So thus, if we draw that on our diagram, magnetic force is going this way. Okay? And the magnetic field, also, which we can apply this electron rule, it'll be tangent going this way along this. It looks disgusting. It'll be tangent to the circle. And now we're going to look at I1. Let's do that. I'm going to redraw the diagram at a lower point. And now we're going to be looking at the magnetic field generated by I3, sorry, not I1. And from that, we should be able to come to get, once again, a force going in the opposite direction, magnetic field that's tangent to the circle, and as well as, remember, the current is going up. And that's just by applying the same principles that I used up here to get to where we wanted. And the point of this is to prove that whatever the currents, whatever we since we want that the net magnetic force should be 0 in between wire 1 and wire 3, that I1 and I3 should be parallel. Or in other words, that's a poor choice of words. They should be going in the same direction. I have no idea what symbol to be using, but I'll just do that. So yeah, that is part A. Let's look at part B. Okay, part B. So part B is, if I1 is equal to 3I3, how should D and D compare if number 2 is to experience a net magnetic force of 0? So this is a lot easier. Like now we have a much easier problem here, and all we need to do here is once again use this thing from Ampere's law, and we don't know what I1 should be. Excuse me. We don't know what I1 should be in terms of I3 or vice versa, but we do know that, or excuse me, the other way around. We know what I1 should be in terms of I3, but we don't know what capital D should be in terms of lowercase d. So we do know this. Mu naught I1 is over, and once again, we can just take a sneak peek at our first diagram. It's over capital D, magnetic field for I1, and for the magnetic field for B3, it should be mu naught, and it says, you know what, let me substitute 3 and mu naught I3, because it says I1 is equal to 3I3. So we just substitute that here. This is for B1. So 3 mu naught I3 divided by capital D, and B3 is equal to mu naught I3 over lowercase d. So all it's saying now is to make these equal, since B1 should be equal to B3 for a net force of 0, which we proved earlier. We proved that right here. Right here we proved that. So now let's go down. Whoops. So now that we have this, we need to find out what lowercase d is in terms of uppercase D. And finally, we can do that if we just look at this, after doing some algebra, it should be that D is equal to 3D. Right. Yeah, that's the answer. So this was number 14. I hope that this helped, and have a good night. Oh shoot, how do I stop this? Here we go.